Thank you, John Beck. Thank you. Yeah, it is. I'm so happy to be here again. In 2012, I enjoyed my time. Okay. So this K-theory gadget, I am trying to learn. So I don't know that much. I'm just trying to apply some theorems to toric category. So first, so title is but if you have any question, please ask me, or any suggestion also, I would love to have. So this is work with Uma. So toric orbifolds, this has like geometric notion and as well as topological notion, but topologically it's a little bit easier to construct, so we'll consider that construction. So to do that, we need to introduce simple polytope. But what is that? This is a convex hull of finitely many points, which should satisfy the following condition, that at each vertex the number of codimension 1 faces of that polytope should be the dimension equal to the dimension of the polytope. So what does it mean? This is simple, so I can just say Pn simple if V is a vertex of Pn, then V equal to the intersection of Fi j equal to 1 to n, where Fij is codimension faces. So let's have some example. It's very to give example in 3 dimension. So we have tetrahedron. So we can see that each vertex is the intersection of 3 facets. So it is easy. Okay, and that n-dimensional cube also here. So I will just see. I think I will have some time. Okay, now I will do something which may need after some time, but this is the easiest notion to say. So we said in our paper with Bahri, which one is first, Song or Sarkar? Huh? Okay.
S-O-N-G.
Okay, Sarkar, then Song. So we introduce like retraction of polytope. You may think that, oh, this is like convex set, so in topologically we can retract very easily, right? Retractable to contractible to a point, but we will not consider that topological contraction. We have some special way to do that. Let's see some example, and we will understand whether we can understand our retraction. So we will take the symmetric object, which we call like prism, 3-dimensional prism. So consider this vertex. This is V1. So what are the faces which does not contain V1? These are faces here and here. So we'll draw that one. So what we did from here to here, we deleted a neighborhood open neighborhood of V1 from this polytope, and that open neighborhood is determined by the complement of these faces, right, union of faces, and that faces is determined by this vertex, right, that this vertex the faces which does not contain this vertex. Okay, so what we could see, the neighborhood of this vertex is looks like R3 positive, right? And here what are the vertex which looks like RK positive for some k. So these are here, so it can be V2, this one and this one, right? But this is not the case, because this vertex is the intersection of two faces, so this is not sorry, not R2 greater or equal to 0. Oh, it looks like very small. Okay, I'll make it a little bigger. But this vertex looks like the neighborhood is R2 greater or equal to 0. So what should be the maximum one? Maximum one will be if I delete this edge, right? So we can delete this face. So we will take this edge now. So we have right. So we are deleting this face from this object. So what we are getting, we can say.
I think you mean face. You deleted the face, not the edge. The face.
The edge from this face, equivalent to delete this face from this union. Good, good, thank you. So this will say B1. This is, I think, Q1 and B1. So what is Q1? Q1 is here as B1. But here B1 is this union, B2 is the union of these two faces, and Q2 will be this face containing this vertex, and then V2. Sorry. Okay. But in this case, we can take, there are four possibilities. So we'll take V3 here. So here, this is Q3, which is equal to again B3. So we have triple Q3 V3. So how far we can go? So we can delete this one. Then it will look like R2 greater or equal to 0. So if we just delete this edge, then this is V4. So this is B4, this is Q4, and this is V4. And so we can go up to point. So this is V5. So B6, which is equal to, this is trivial but it is necessary to say. Okay, so this is B5, Q5 and V5. Okay. So if it happens for more generally, so this is for prism, what we could do for cube also, we can take this point, then the remaining will be like the faces, union of faces which does not contain this one. So and we can go this way. Is it okay, this construction? So we say like retraction of polytope, not in the sense of like basic topology we do, but this is, so what it does, it preserves some face structure. So that is important to our construction. Okay, now we need to define what should be toric orbifold. So let's F, I said P, n equal to the facets of F, okay, I think M we need B, the facets. Facets means codimension one face of Pn. So now the question is whether we can define this function F1 such that it should satisfy something what is that? That if fi1 intersection fil is not equal to empty set, then the corresponding vector fi1 to fil is linearly independent. Is it okay? So this is a characteristic function. Characteristic function on Pn. Now given a simple polytope, whether we can define this kind of function. So this is always possible, because if we see first if we consider a vertex, so this will become n many facet, so we'll assign, because we know Zn has n many linearly independent vectors. First we will assign that, then we will go to the next vertex, then at this vertex how many we know? The known vector is n minus 1, so that n minus 1 will generate n minus 1 dimensional submodule, so we can choose another complementary dimension. So in this way we can define. So use the fact that if we take the finite union of proper submodule, then that cannot be the whole module. So using that we can define any a characteristic function on any simple polytope. Okay, so let's take f be a face of Pn of codimension k. So that means dimension is n minus k. So that is dimension f equal to n minus k. But since P is simple, P simple will imply that there exist unique facets fi1 to fik, which is a subset of script Pn, such that unique collection of facets, yes, collection of facets, so that f is intersection of fi1 to fik. Good. And now we know that each fij corresponding to this we have a vector. So fij has association fij. So we can just say in short jij. So what we will get corresponding to this intersection, we can associate a submodule generated by ji1 to chi ik, which is a submodule of Zn. And now we'll say this is M of F. So this inclusion that induces a matrix. So that is, I'll just write a homomorphism. So that is given by tensor over Z quotient by MF, that goes to Zn tensor R quotient by Zn. And this is our well-known object, so you can think is as a n torus. So we say this is our Tn, torus Tn. Okay, so this image, so that is we can denote by small f and this. So what we can do, we can define a torus Tf equal to image of this map. So this is subtorus of Tn now. This one may not be the subtorus of torus, this Tn, but the image is a subtorus. This may have some problem. Okay. For example, like if the rank is same, if the rank of this one is same as this, but this does not equal to this one, then this is not the subtorus. So that become like some finite covering. So that may case happen. But the image will always be a subtorus. So TF is the Tn is subtorus. Okay. So now we can use DJ construction. So DJ so what was that? There are 19 one paper that we have Tn, we have Pn. Now we want to define an equivalence relation. So here is S X, this is related to T Y if and only if X equal to Y and belongs to the relative interior of the face F, such that S T inverse belongs to TF. So it makes sense, that identification. So what pictorially we are doing for two-dimensional case, see if we see example for Pn equal to just the interval. So we have circle here S1, which is T1 cross. So we need to assign some vector, but here okay, what we want to assume that Fi is primitive. That means GCD of the entries of this vector is equal to 1. So what should be the one possibilities? Like just it goes to 1 and this goes to 1. And the circle subgroup, so if it is F1, this facet is F2, then TF1 equal to just S1, which is equal to TF2. Right? So if we just do this identification, so what it is saying, we had this cylinder, so this will be and then we have identification, but that identification is saying that we have to collapse these two sides. So it will become this point and this will become this point. So you get like topologically S2. So you can just say. So in general, what this construction is saying, if we take a polytope and along a face we are collapsing one circle subgroup of torus. And it turns out that what we can show, this we will denote by X, P n chi equal to Pn cross Pn is an orbifold. Actually here effective orbifold we can say. Effective. So what do you mean by orbifold? It's like Y, okay, Z is an orbifold. Oh, Z we took, so Y and orbifold. If we take an element from here, there is a open subset containing U, so Y belongs to U, which is subset of here, such that we can have another subset U tilde, which is subset of some Rn, and a map here such that U equal to U tilde by some finite subgroup where G is finite and G is a subset of diffeomorphism U tilde. So what it is saying locally, it looks like the quotient of finite quotient of some open subset of Rn. So what should be the example? Say if we just see this polytope, then we can see, suppose this vertex. This vertex has a neighborhood which looks like R3 positive. Okay? But R3 positive, how we can see it? We can say, if we take R3 with the Z cube action, where the generator acts as a reflection, then the quotient become R3 positive. Right? So at each point we can find this type of neighborhood. So this is an orbifold. So each polytope is an orbifold.
I don't think it can be any open subset of Rn. It's got to be a special open subset of Rn.
No, it can be any open subset.
Well, take an annulus.
Yes, that can be also true.
Does that the definition of still fit the definition of orbifold?
Yes, it fits in the orbifold.
It's got to be disk-like.
No.
We can't even agree on what an orbifold is.
No, that can be also possible, because if we take like this with reflection, okay, and so it will become R2 greater or equal to 0. So that is this one. So what should be, how we can choose the orbifold structure here? There are several possibilities. Oh, so here is R2 positive, right? So it looks like this. Now if we want to define the orbifold chart over here, there are several possibilities. So we can just take this one and then the trivial group acts. But we could take union of this, so that only that group G will be like just a reflection.
And then mod out by reflection.
Yes, we can do that. So if we just take the annulus here, then it will become.
Doesn't even give me an open set.
Why not? Here it will become like this.
It's got a boundary.
That is.
If I
No,
take
it
the
doesn't.
quotient- If I take
That's
a,
open set.
Yeah.
if I take a quotient of the open annulus,
Huh.
let's take. So
Yes,
the
yes.
origin,
You can take the open
the
annulus.
action is, the group action is reflection.
Huh. Yes, Tony. So it.
No, this is open.
Manifold
It is.
corners or
Yeah,
something.
that's
So that is open set in orbifold. So the orbifold with boundary has little bit complicated notion. I can tell that, but I don't need here. But this is open
Class of
and this is
objects
open.
You're discussing there. It's
Uh-huh.
a general class of objects.
General
Yeah.
class of object. So that is good. Okay, so we have now toric orbifold. This is called toric orbifold.
How would you make this example here in S2 as an orbital? You are, but by this construction.
Oh, here it become like S2, no orbifold structure. No, then want. Yeah, by definition, we don't have any orbifold structure on.
Yeah, that's because if you take a two,
Huh.
see when you take a disk and you mod out,
This is the reason why you are taking primitive.
Yes,
That's the reason.
that's the reason. So if
And
we
you
just
cannot
take,
get, by this construction, you
Huh.
cannot get the orbital.
we cannot get the orbifold structure.
if you, in
But-
the case of a two disk, see if you take an ordinary disk and you mod out by a finite group, that's not necessarily a disk, it's contractible.
Yeah.
It's contractible, but in the two-dimensional case, that doesn't happen.
Yeah, if I just use this construction, then toric orbifolds over
Your definition
little bit.
leaves out most important simplistic.
Simplistic. To make our life little bit easier. Because
If we just lift the condition that this Fi, the characteristic vector, is primitive, what happens?
if it is not primitive, then we can say
You can still get this orbital structure.
yes. Then we can get the orbifold
You
structure.
have some problem in other constructions.
Yeah, there will be some.
To use the information in the retraction sequence, we need
So
primitive vectors at each stage. We need to choose primitive vectors,
otherwise it
can't
is.
test the condition we use.
But without
may-
that, just not assuming that it's primitive still works.
Yes, that will be like
Yeah, so
Change the orbital structure.
yeah,
so
that will
I-
change the orbifold
instead of-
structure.
Instead of imposing this primitive condition from the beginning,
Huh.
we just make everything general. And then for your
At the end.
construction, from now on, we will assume that the checklist vector is primitive.
Actually, do you, in this paper, in this K-theory paper, are you using that it's primitive?
Yes, we need to do that. Yes, that is one of the important things. Otherwise, see, it will become a rational cell, not the actual cell. That is the problem.
When you talk, everything depends on divisibility, right?
Yes.
Everything depends on things being divisible. And if you don't take that, then
Right,
it's
I
doesn't
understand.
work.
Huh.
My argument is that from
So-
the beginning, when you give the definitions, make most general so that it can cover everything. And
And then
for your result,
Yeah,
you give condition.
it's like
That's more, reasonable.
what we wanted to do, like for example, we have weighted projective space as well as fake weighted projective space. So we wanted to avoid the fake one. So we assume that okay, this is like primitive. Otherwise, it will become like in odd dimensional, it may have some torsion.
That's a good example. You could, Soumen's example is a good one. You could take weighted projector space and you can multiply all the weights by some. You don't change the weight, even geometrically, you don't change the weighted projector space. But the way you analyze it is very, very different. If you do
Yeah,
that,
it will have
you
some
common
complicacy
factors.
in the cohomology calculation. So that's why.
No, I'm not going that far. I'm just, when you are giving...
Yes, that I agree. Yes, I
you are
agree.
giving, from the beginning, you are giving too much restriction.
Restriction. Yes. Thank you.
Yeah.
I think
for
we
your,
need it.
For your purpose, you
Uh-huh.
give further restriction
Uh-huh.
as a condition.
Yes, that's better. Thank you. Good. So now, if we remember, we had this TF. Right? So corresponding to this MF and TF, let's see what we can do. So MF. So this is a submodule of Zn over Z, and rank is, so this has rank K, right? That was codimension K. K many vectors is here, so rank is K over Z. But what? Since it is like linearly independent, this may not be the direct summand. So that means there does not exist. There may not exist a submodule of Zn such that this MF direct sum A is isomorphic to equal to Zn. Now, but we want to make it. How we can make it this one? So we have M star F. So what we can do? This MF tensor R over Z. So now this will become subset of that will be subset of Zn tensor R, and then we can take the intersection of Zn. So what we are doing like, so it has some lattice point. Right? So it may have these things. Oh, this is a little bit bigger. So what we are trying to do, we make it like a continuous hyperplane, and then we are taking the intersection with the biggest lattice, so that if we had some vector inside the fundamental region of this, that will belongs to here. So what does it mean? What it is doing, the area of the fundamental region here, if it is more than 1, then what is a parallelepiped determined by some generator will contain some other vector of Zn, which may not be Z linear combination of that, but rational combination. So we want to make that Z linear combination. So it will become again rank K submodule of Zn, but now this is a direct summand. So there exists some A, so this is equal to, that was question, now here it is some A exists, so that this is equal to Zn. So that means this is a direct summand. Direct summand. Okay. But from here we can define one. I'm not sure whether I need it. I think I don't need, but it is another observation. So this will be a finite abelian group. Right? Okay, now consider a vertex V. Before that, I will just say. So since F is a face, F a face of P, F is also a simple polytope. Okay. So we can consider facet of F as a simple polytope. So we'll just say H12, which I didn't say, HL, HR. So this is facets of F. But what should be the relation between this facet of F and facet of P? So if I take Hj, so then this is equal to F intersection F J L. Yes, for a unique facet F J L. Oh yes, you're right. Thank you. Yes, I sub j, F I j. Okay. So now, since this is a direct summand, it implies that we can have a map from Zn to Zn mod M star F. And what is the speciality here? This is isomorphic to Zn minus K. See, if I say this is rho F, then we can define a map from which we will say chi F from F to Z n minus K, and by defined by F H J, we can see that H J here. And what is this one? This is intersection of this, but we know chi of F I J. So first we will apply that F I J, but this belongs to where? Zn, right? Now we will go there. So we will compose here rho f of z.
Do have an listing
Now,
there, but why don't you use A? Zn mod of m star f.
oh yes, we can say that this one. So this is isomorphic. Oh, thank you. But this is
So
exact.
is from Zn to projection.
So that will become a, that is isomorphic to Zn.
So
Now-
it's just a projection. Go ahead. It's a projection into A.
Projection onto A. That's good, thank you. Now we can see, as Professor So is saying, that it is better to take this one. Here we can see that it is better to not assume the primitive one, but even if we assume the primitive one and use our construction, then the characteristic toric orbifold we will get, both of them will be isomorphic. So this will be, so this may not be primitive, right? After, if we just do the projection, this vector may not be primitive. But if we consider this vector and do the construction here, then the orbifold we will get, suppose that orbifold is x of f chi f. And if we assume the primitive one, and construct again the same thing, so I will just say x prime f chi f. Okay, I think here I should say primitive to distinguish little bit. Then what we can say, I think BSS, we said that they are homeomorphic. So that's why it's okay. So if we don't, first condition is, if we don't assume that this is primitive, then we will get this toric orbifold. And if we assume primitive, then we will get another toric orbifold after the construction. And we can show that they are homeomorphic, equivariantly homeomorphic. So orbifold, as a orbifold, I mean as a topological space, they are same. But as an orbifold, they are different structure because of the local chart. Okay. So as a topological space, homeomorphic as topological space. So that was.
In other words, you originally had the characteristic function, but even though this characteristic function is primitive, its projection to the base
Yes.
is not primitive.
Yes, it may not
If you
be.
mod out this vector by its length,
Yes.
then you
Then-
get another
Characteristic function, exactly.
And then you have x prime.
Yes, then we have x prime.
So that's why I said.
Yes, yeah, that's why
you are prepared.
That's why I mentioned that.
Because you are using this
Yes,
non-primitive vector.
non-primitive. We said in our paper also, but that was good. Okay, so now
You are constructing a orbifold which does not assume this primitive.
yeah, in the middle again it is assuming that okay. Okay, good, thank you.
Would complicate the argument a little bit.
Yeah, that will complicate it.
Complicate it. And not in this paper so much, I don't think, but in our paper, that would complicate things. In fact,
Yeah, I
if
think
you, it's for later.
I understand.
It's for later. This is, Sherman and
Just
I
for the
differ
construction, it's
slightly on how. Sherman loves lattices, right? I love tori and this construction over here. And they're not, it's not quite the same point of view, but Sherman's point of view is very precise.
Oh, as Tony said, so
No, not even
Remember.
that construction. That's a very bad construction.
This is like combinatorially looks nice, but we can write this as a quotient of, we say, moment angle complex. So by some t n m minus n.
But you can even do better than that. You can
We can
do that Davis-Januszkiewicz construction where with the tilde, see the tilde there? Without lambda in the tilde. Without lambda in the tilde. And it gives a very clean description of exactly what's going on. Also in the Orbifold case, but we take this point of view here, which is a very nice point of view.
Since you this hit stopped you, you said when you mentioned about the characteristic function, you said did you say you can always find characteristic function?
Yes, yeah.
No. Is it?
Rational characteristic.
If your polytope is very complicated, even the rational, I'm not so sure whether the rational. So it's in between you and us. This characteristic function is, we say, rational.
Yes, rational characteristic function.
Does that guarantee that?
Well, fails to span, yes, fails to span. Everything is measured, everything in the subject is measured by the failure to span.
Yeah.
By the quotient of
What
lattices.
about this, the example in this Davis-Januszkiewicz paper about this?
That is for manifold case. But if we consider orbifold one, then we can define.
Okay, we will talk
Yeah.
about it.
Okay, now if we consider a vertex V, then as a face vertex of F, V will be the intersection of H, J, L equal to 1 to n minus k. Okay? So what we will get, now we are assuming, so we may assume that this is primitive. May assume this is primitive.
What condition can you get? What makes this vector to be primitive? What condition should be given? I mean, even though you originally got the primitive vector as from the characteristic vector, but that does not guarantee you. If you project it down, that does not guarantee you.
Yes, yes.
So
Many.
Can you get some of the sufficient condition how to get this one to be primitive?
Say again.
No.
I mean, you just assume that this projection, this will be F.
No, we not have.
Primitive.
No, he takes the projection and then he chooses, that gives some vector, right? That gives some vector.
Yeah,
and then he takes the primitive vector. That's part of the operation.
No, but he is asking whether there is any guarantee that we will get primitive vector. There is no guarantee. But this lemma we.
If this is not primitive, you just simply take the unit vector.
Yes, that primitive one. Yes.
You have to be very precise about that.
Oh, okay, that's good. Yes. So
You
that's.
can always do that, but the question is whether exactly that vector projection, or you just take this.
Oh no, that the primitive of that.
Projection is
So.
complicated actually.
No, I
to write
understand.
the projection
I
explicitly,
understand
you've got to go around
Okay.
choosing
If
a
you are,
good
Okay.
just don't
So.
assume that, but just make this one.
Yes, so that will be, this map will be primitive of
Otherwise, it's confusing.
primitive of this rho
Choose the primitive
F.
vector. So that's what you have to say. Right?
Yes. Thank you.
It's primitive, I agree.
How many? 1, 2. This.
So maybe low bar might be taking primitive vector. That doesn't matter. Okay.
Yeah, primitive of this one. That's good. Yeah, we cannot say that is primitive, but okay. So this will be F I H J 1. So rho F H J n minus k. But what is this one? This is vector in here, Zn minus k, right? And how many we have? N minus k. So we can construct a matrix whose column is the transpose of this. Right? So we can say, okay, what should be the determinant of this? So we just said this is determinant is called G F V. So F is the given face, and if V is a vertex of F, then we can find a finite subgroup.
It's little g of f of v.
No, little g is the mod of
The determinant.
G F V is our G F modular.
The capital G stands for definite group.
Oh, determinant.
This is a
is it? Ha ha ha.
So you-
Okay. Thank you.
so
Thank you.
mean the
So,
absolute value of
absolute value of this
okay.
is this one. Okay. So here is importance that we need primitive one, because, for example, if I just say this one comes as a phase of some after some. So if this is a phase, and if we consider this vertex, then what will happen? We need to cut this vertex. So at some point. Now if we don't assume that this is primitive, then it will become like, as we know that length space, but there will be some orbifold structure, non-trivial orbifold structure.
Similarities of the orbifold comes from the vertex of the polytope,
Yeah.
and then somehow this number GFB has this
Information.
structure
Yes.
of the polytope,
Yes,
of the orbifold.
Orbifold,
But
yes, yes.
the critical point here is when you start with the big orbifold, these numbers have divisibility, right? They're divisible by something. Now, when you the critical point here is when you restrict to a smaller face, right? And then you make the toric orbifold corresponding to the smaller face, and then make the same numbers corresponding to the smaller face. The divisibility goes down.
I understand.
Yeah, that's a critical
So
point.
here, for each vertex, the vertex is a face for many different faces.
Yes.
So for the V vertex can be a face of facet, but face of
Edge.
smaller dimensional. So for
Face.
each face, you have this number.
Yes.
So for one you have a sequence of
It's-
Yes, yes. So
But the divisibility of the number goes
Huh.
down. All
So
the
if
numbers
F is
by
a
the big one, right?
face of,
That's why it works.
so yeah.
then if it happens,
If the divisibility didn't go down,
then
there would be no theorem.
G F V
Because
divides
the vertex
G
is singular.
F prime V.
The orbifold, this singularity has a group associated with
Yes,
this singularity.
yes.
And this group is not just a
Oh,
number, but
this is
it has many
other way.
structures. But here, for this vertex, has many different numbers. So that's, in a sense, associated to the
You
group.
see, this is coming from, when we say in the subject, when we say the kernel of lambda, we use the phrase kernel of lambda, right?
Okay.
But you can't do anything unless you represent kernel of
So
lambda
let-
as a subgroup of T3n,
Bn.
right? The big torus. You have, and when you write it as a subgroup of the big torus, that contains all of this information.
Yeah, that's what I'm saying.
Okay, let's see this one. B A. So this is a toric orbifold, and that be a retraction of Pn such that this G, now we have Qi Vi equal to 1 for I equal to 1 to number of vertex we choose. Okay, I can just say this one. So we have that retraction. So corresponding to that we had fixed vertex and the face containing that vertex. If it happens, then we call X Pn xi is divisive. orbifold. Okay. Now I should note how. I think I need to delete this. Now let's see how we can construct.
Not divisible, divisive.
Divisive, yes, divisive, not divisible. Okay. Now let's see how we can construct this toric orbifold. So that was one a little bit more geometric, but here suppose we take a tetrahedron. So I think it's better to take triangle. It's better to take triangle. This picture is much better. So what happened here? What should be? So this is a face F total. Then what will be TF? TF will be just T2, right? T. Now if we consider this is F1, then this T F1, right? We will get this TF1, and here this is TF2, here it is TF3.
Generically.
Yes, then this is TV1, TV2, which is equal just trivial, right? So this.
It's a really confusing point. But I goes to 1 to the vertex of Pn. It's not necessary, right?
Yes.
Retraction.
Up to edge.
Cover.
Up to edge is okay, but
The sequence of this retraction, does it cover all vertices or some vertices?
No,
all vertices.
It should cover all vertices.
All vertex.
Yes, but the
It should,
divisibility is
but-
going down. See, it's Q, the critical point, which is not written very distinctly, is it's G sub Qi. G sub
So
Qi.
it doesn't retract anything about the point.
No.
Okay.
Oh yes, anything.
Within the
So
sub,
I
up to
understand.
the sub.
up to the
So if
edges.
you have a retraction sequence, it should cover all vertices.
TV3. So now what diagram we have? We have this one. So we have diagram of inclusion, and this includes here, this includes here, that includes here. So what we can do, this is, we can make the limit of this diagram now. So this will be limit of this, okay, limit of this is equivariantly homotopic, equivariantly homotopic to our x. Here is P2 chi. Okay. So more generally, if we have a face, then we can define this one. So that face, that torus has an inclusion in the bigger torus, so we can get the diagram. So how we can do that? So in general, it is okay. Little bit. This diagram is okay. So we had that torus, right? Polytope, and on triangle we had. So if we have this one, map Z2, right? Chi is there. So corresponding to each face, we can define this subtorus of Tn. So this depends, this torus depends on this characteristic function. So you have diagram, then we can consider the limit. See, here is this one, so it's better to have limit, not the co-limit. Okay, so this will.
Is this diagram in the category of toric?
This is a category of toric object. So in general, what we can do, so if we have Pn and F is a face. Oh, I made mistake. So that is not TF. That should be T mod F. Sorry, T mod F. So that is.
Because it's just TF, then it's not.
It does not give any torus. Oh, sorry. So this is T mod TV. Oh,
Yeah.
that's why it will be.
That's what I was
Oh.
It's just saying that it's a finite bubble where some of
Yes, yes. Oh,
collapsed.
I was a little bit hurry. So T mod this. So that's why it is. Okay, this is not trivial, but T mod this is trivial. Okay, so T mod this. So if F is a phase, then what we defined? TF, right? If we remember. So that is subtorus of T. And now we can see that why we needed to have subtorus. Then we can define T mod TF. So F goes to this one. So what we will get if we say defined category of Pn.
TF gives, if TF, you have any information about TF, then you automatically have information about T over TF.
Yes.
Why do you need? I was confused, but TF2, still TF2 is the image of this.
The reason is this T mod TF, it is alive. Right?
It's using the characteristic. That's using the characteristic.
Characteristic.
heavily.
So that is subset of this one.
TF is the image of that.
Huh.
So let's see.
It's defined
So how-
by the characteristic.
Now if we just see this construction, so what we are doing, suppose a vertex we took. So vertex, at the vertex it will be Tn cross that union at the neighborhood of the vertex, but that is exactly will be equal to the homotopy limit of these two. So this goes here, this goes here. So the homotopy limit will be this torus union this torus, but homotopy means I can extend up to this vertex.
You see, it's up.
And
You're
this one.
not just. I think you're taking. Aren't you taking a homotopy limit here?
Yes, yes,
Yeah,
that is.
you need to say that because. Well, it's not the same as saying you're taking the homotopy limit because a different construction. Because you
Okay, I am telling again.
Yeah.
So
I think
cat,
you've gotta say
so this is object of this is faces of Qn, it is Pn, and morphism in this category of Pn equal to the inclusion F is included to I F prime, I will say iota F prime, just inclusion. Okay, now we will get this. So what we will get? We will get a map from this category of Pn to topological space, torus TS spaces. And how we are getting? We just said, okay, F goes to T mod TF. So this is, if we say this function as a nu, then X is homotopy colimit. Then
You've got to say what the maps in the diagram are, so we can assemble them into the topological space.
here.
TF is just a torus, isn't it?
Yeah.
Yes, we have just have torus. That is torus. Then this X Pn I is homotopy colimit of this nu. How it is coming this homotopy? Because this is at one point, but we can extend it up to this face. So
In the homotopy colimit, you're multiplying by
By-
simplices and taking also.
yes, by interval, yes,
complicated maps.
simplices
So you're
and
thickening
taking.
it.
Yes, we are thickening this,
into the top,
and then
the toric orbifold.
we are doing the colimit, so that will be like union here, since it is a small element in a small category, so that will be just union. So you can see this one. Now what this Peter May said in his book, that if we have nice topological spaces in the category, then we can have a map, commutative, differential commutative graded algebra over Z. So this is if we have E orientation, complex orientation E, then we can have covariant.
Whose book did you just make?
Peter May, that was equivariant homotopy and equivariant cohomology. May, I think, 96, I guess, book, I should say. Okay. Book. And chapter maybe, that is very difficult to say which chapter. Still, I could not understand which chapter. I'm reading this one for this last 1 or 2 months. So chapter, I think 7 or 8, 7, 8. Sorry. So if we just take the composition, we will have map from here to here, and that gives our mapping that F goes to E star, the equivariant, I should say more precisely ETN, ET, F, so which is equal to E star T of T, TF. Now how we can define this one? So I just wanted to say, but it seems time is over, but still I will say in one or two sentences. And using this functor we can, and some result of Harada-Hendricks, we can compute the equivariant carrying. So what is happening, suppose we have this edge, and this edge, if I just forget this one, so this is nothing but, so if we take this one, so this will be open, and here we just have circle bundle, the same circle bundle. And now how this torus is acting, the bigger torus is acting by some character, and that character is given by the complement of the this characteristic function determined by this phase. Okay. So in general, if we have edge E equal to Fi1 intersection Fi, sorry I am taking little time, but I think this is one of the important points which I didn't say in Moscow, but this is, so we will get chi I1, so chi I n minus 1, but this is vector in Zn, so we can define a map from Zn to Zn minus 1 determined by this vector, where we will take this as a column vector. So if we just take this matrix, so xi I1 transpose and xi I n minus 1 transpose, so this will give one matrix. So this is n by n minus 1 matrix. So if we just apply this one, we will have this. So it should have some non-trivial kernel. Kernel is isomorphic to,
That's n by n.
oh sorry, minus 1.
The size is strange.
N minus 1, this is.
N minus 1.
Then this.
So if we apply Z,
Then that's a z n minus 1. This matrix represents z n minus 1 goes to 0, right?
oh I am applying here.
No.
So
No, plus
A1 to AN. So if I just apply.
left multiplication. Oh, that's
Okay. Then I can take the transpose and.
there is a person whose name is Binkbeiner. He was written a book about linear algebra where all multiplication matrix size is completely upside different.
Oh.
And that's
That makes-
when I was in the college. And that makes me very confused.
Oh, okay.
Makes the determinant indeterminate.
That makes
No.
algebra a non-linear. So don't use that notation.
Okay.
Why
Then
don't you transpose? Just do it.
okay. Then I can just take the transpose of this transpose. So it is same as this. Since I took that row vector, so we'll have this. So what we can have? We can have a generator of this. So this can be generated by U. So U can be primitive now. We say primitive u. So what will happen? So this T action on this, so T action here is determined by this u. Okay, so this u. So this is our character. So this gives T goes to S1. So after some computation, like since it is circle, the T mod T E, this is circle, so we can consider it goes to disk, corresponding disk. So disk T mod T E, sorry, and then we can make the thumb space of this one, so that is exactly equal to D T T E quotient by that T mod T T E. It's little bit complicated, but then so this is a cofibration, equivariant cofibration, so we can consider we can apply this vector, this generalized equivariant cohomology theory, but this is contractible, so we'll get an isomorphism in E star T and I should say thumb space of this T mod T E. So this will be isomorphic to that E star of T E E quotient by equivariant Euler class here. So E of I should say E comes many times, but let's say T E. That E is not the same as this E. I may have to put some little bit bending, but I cannot do it now. So this is isomorphic to E star of this thumb space, isomorphic to E star T of this one. But this is we can define because we know this character. So that Euler class is determined by this character. So it will be 1 minus e power this character. So that is well defined. For each edge we can do this. Now if we consider a retraction corresponding to this, then we can define a filtration in this toric orbifold. And using that filtration and result of Harada-Hendricks, we can say what should be the cohomology, generalized cohomology ring. That will be exactly the co-limit of that where we defined. So it is co-limit of this. Now corresponding to each phase, we can define this type of piecewise algebra. So this is for edge E. So more generally we can define for any phase. And then we can take the limit of this piecewise algebra. So this limit of this piecewise algebra will be isomorphic to the generalized cohomology ring of this because of this observation. So
Chairman,
that's maybe.
In the smooth case, what is that expression at the bottom? In the smooth case, how do I see the Stanley Reisner ring? If I take the smooth, if the orbifold is smooth, the orbifold is smooth. How do I see the Stanley Reisner ring in this algebra?
If the orbifold is smooth, then what happened? We have another vector, right?
Yeah.
So that will be like determinant plus minus 1. So that vector will be generated by this.
By the way, this sorry, but this time
Too much time.
the classes.
It's not a 2-hour seminar?
No.
1 hour.
John Beck said it was 2 hours.
No.
No.
I have a.
So-
those people. Have
Sorry.
I too have classes.
I'm sorry.
So,
But
this is
But-
already 10 minutes. After.
yeah, but that is main point that we can do.
Right. Yeah. Right.
Okay. Thank you. So is that theorem is okay? Theorem says that generalized cohomology theory of this is the limit of this type of gadget. That piecewise algebra. Okay, thank you.